This material that we're going to cover in today's video is so much fun for me because my degree is in pure mathematics, and so we only really work with theory and very, very little with actual applications and real numbers, so to speak. So this is my bread and butter, and it's kind of like a double-edged sword in the fact that some of this stuff outwardly appears to be so simple that a lot of time people ask, well, why do we even have to do this? And what vector spaces are about is about reminding everybody that, like when you drive a car, you get in your car, you drive the car, and the car works. And it's very seldom that people say, well, how come the car works? Why can we do certain things? And so vector spaces is kind of the same thing, but for math. It's one of the first times where we take a step backwards and say, all right, look, hey, we've been adding vectors, we've been dot product being vectors, we've been doing matrix stuff, like we've been multiplying numbers, we've been able to do all this. How come we can actually do all of this? Why does it work? How come I don't have to check whether or not I need to, whether or not that 2 times 3 is actually equal to 6, or that if I add 2 vectors together in the third vector, that it's always that way for every vector? How come we can just do it? So a vector space is kind of the name that we apply that generalizes like this kind of space that we're hanging out in, that the rules of mathematics as we know them, and by we, I mean, you guys and the exposure that you have to math, that the rules that you are comfortable with actually hold and work. Because you may have noticed, right, for instance, that when it came to multiplying matrices, we like multiplying the 2 matrices A times B, it was not always true that B times A was the same thing. And, that should be a little bit jarring because you spend the last 10, 20 years of your life, doing math, just thinking, okay, A times B, P times A, no problem. And then all of a sudden we start doing math with matrices and we say, well, hang on a second, that's not always true. That should be a little unsettling. So we're going to kind of dive into really describing what a vector space is. And the idea is that after this, you'll have a bit of an appreciation of kind of like the level of effort it goes to really even make the math that we're using possible to use. And if you're into theoretical math, or maybe if you've been thinking about it, this will be like your first real taste at doing some hardcore theory. And if not, well, that sucks because we've been doing applications for the last few weeks and it's time to get into the theory. So first things first, we're going to bring up a definition. So definition. All right. A vector space. A vector space. A vector space is a non-empty set. So a non-empty set V of objects, which we call vectors, we define 2 operations, and only 2 operations. And we're going to call these operations called addition. I know, very next level stuff. And multiplication. Right? Those are the names of these special operations that we're going to introduce on this set of stuff. And multiplication, not just by anything, by scalars. By scalars. Okay. And these vectors, these objects in this set, so these vectors are subject to the following 10 rules, or what we call axioms in mathematics. Following 10 axioms. These are just rules. And, it must hold all 10, so all 10 must work for every single vector in our set V. Okay, so, you know, this is kind of hard to provide a tangible example right off the bat, but the general idea is that we are going to have a collection of stuff. And this space, we call it V. And inside this space is stuff. There are vectors. Now, notice that I'm not saying that the vectors look like this. I'm not saying that they look like the vectors you and I know, because it turns out that, maybe a vector in this space might be a polynomial like 2x plus 3. It could be that a vector in this space looks like some matrix, 1, 2, 3, 4. It could be that a vector in this space looks like just some number, right? It could just be the number 2. It could be that the vector in this space is defined to be a vector like you and I know it, right? It really depends on what the objects are in here. So the idea is like, if you decide that you want to do some mathematics, and you're like, hey, I have an idea for some math, and it's going to be super useful math. The idea is that, okay, you can create a little space, and if you satisfy these 10 axioms, then you can more or less do math that you and I are already kind of comfortable with. And if you don't, the idea is that then your space isn't a good space to do math in, and you need to modify it a little bit. So what are these 10 axioms? Let's write them down. Okay, so the first thing that we would like to be able to do, and maybe I'm gonna redraw my little space over here. This is my vector space V, and inside of it are going to be vectors. So V1, U, W, V, I don't know, or maybe I shouldn't use V because that's my vector space name, X, Bob, right? Who cares, right? These are just all my different elements. They're not necessarily vectors like you or I have used for. The vector is the general term for one of those objects. Okay, so the first thing that we want to be able to do is that if there are some elements, so if there are two vectors UV that are in my vector, my set, my ideally my vector space, but technically we don't know this is vector space, so that are just inside my set V, what we would like to happen is that then U plus V is also in that space. The idea being that, if I add stuff together here, that it's going to pop out a new vector that is also inside my space. That C doesn't exist outside the confines of the rules or the structure that I'm trying to implement on these objects, right? Because if you really think about it, if you were trying to discover math for the first time and you were just like -3 pi e, and you're like, gosh, I wanted to find some rules so that all of these things work in harmony and they allow us to do stuff like build buildings, you might sit here for a really long time and really have to think, okay, what do we want to be able to do? All right, I want to be able to add these numbers. So I add 2 and 4 and I get 6. Oh, but 6 isn't in that set, right? 6 is outside. Then you would have to go about and show that 6 follows the same rules as all the other objects that are already in this set. And that would be like a super big waste of time. So we want, if we're working with a good set of objects, a good set of vectors, we want to make sure that the number that comes out of here exists in that set, or the vector that comes out exists in the set, and it also plays along by the same math rules, right? So I don't have to, be worried about whether or not this new creation that I make is or is not going to follow all of these rules. Okay, so that's like one of the first conditions that we want. All right, next condition. Let's see, what else would we like to be able to do? We would probably like to be able to add things in any order. So again, given U and V in W, we want, so following this one, you can copy this down in your notes, but given two vectors U and V in our set W, we want that U plus V is equal to V plus U. And again, that seems to be like, you're like, oh, that's common sense. Yeah, it's only common sense because you have done it your entire life without making sure that works. But again, you've already got your taste that it might not be the case that u times v is equal to v times u. It may not be the case, right? Oftentimes, either things don't line up, or the matrix sizes are wrong, or the vector sizes are wrong. So, it should at the very least not be too unbelievable that you could define a collection of objects where maybe this actually doesn't even hold, in which case I would say you are trying to create a bad collection of stuff to do mathematics, okay? You want to pick a good collection of stuff. And I think along the way I should probably write the name of these. So this property here is called the closure of V under vector addition. That's pretty self-explanatory. The idea being that, if you add vectors, you stay within V. Hence, V is closed under vector addition. This next property here is called the commutative property. The commutative property for addition. Okay, we want to make sure that this holds as well. Okay, yes, there are 10 of these properties, and yes, we are going to go through every single one of them and kind of explain why we might care about them. So another one that you may remember is there's commutativity. There's also associativity, and associativity is, again, so given, now we're going to say we have three vectors. Well, I'll just write it down. So given three vectors u, v, and w that are all from my set V, then we're going to say that if I were to add u plus v and then add w afterwards, that's going to give me the same answer as if I did u and then I added v plus w. Again, this is going to seem like no kidding, right? Duh, like this is super easy. But, just from a mathematical standpoint, we have to define these rules, right? It's the rules have to exist, because what we're essentially doing is we are creating structure. We are creating the foundation for the house that you are going to try and build and do all of your math in, right? If you don't have a foundation, you're not going to be able to build this house, okay? So this property is called, as I mentioned, the associative property. Associative property for addition. So we need that to hold true. Let's see, on to the next one. So 4. All right, number 4. So there has to exist some zero vector in V such that if I take any vector u and I add this zero vector to it, I just get u back. Okay, that's the idea. This symbol here, in case we're not sure, this means there exists. This backwards capital E is there exists. And this property, this is called the additive identity property. Additive identity. Right? The additive identity is in the real set of real numbers is just the number 0, right? If I take 4 plus 0, I get 4. It's the same thing with the vector spaces we've been currently exposed to, like R2. If I take the 0 vector and I add it to any vector like 1, 2, I'm going to get back the vector 1, 2, right? So, believe it or not, it's actually important that 0 exists in our collection, right? You can't just make a random collection and not have some vector in it that has this property, okay? Well, actually, I'm not going to say what I was just going to say. It's going to confuse you. Okay, so number 5. Let's see. What else? Oh, well, if we have an additive identity, then it's probably a good idea to have an additive inverse. So let's see. We're going to start using some shorthanded set notation. So for all vectors u in our set V, there exists what we're going to say is a negative u in our set V, such that u plus this negative u vector, if you will, is going to equal the 0 vector. And this is what we call the additive inverse. Additive inverse, okay? And again, you're like, oh, if I have 2, then I'm going to add -2 and blah, blah, blah. That's great, yeah. But if you were, for instance, to tell me, right, so far, let's say you tell me that the collection of numbers 0, 1, 2, 3, 4, 5 is a vector space, right? You're like, yeah, I can do all the math that I have ever known and loved, and it's going to make total sense, right? Well, guess what you can't do here, right? There does not exist some, for instance, if we pick 2, there does not exist some -2 such that 2 plus -2 is equal to 0, right? That doesn't exist. And that's going to disallow us from doing different sorts of math. When we talk about like inverses and things like that. Like this is not good. If you're only restricting yourself to 6 numbers and you're saying, hey, this is the playground. These are, this is all the math we can do, right? We're closing our worldview and saying the only math we can do in the entirety of the world involves these 6 numbers. I'm going to say, well, this is a pretty bad space. This is a pretty bad set of things. Then this is not a vector space, right? Like it's a space, but it's not a vector space. So this would not be a good collection to try and establish a branch of mathematics off of. Okay, moving on. We're on the last few now. So number 6. Let's see. We're gonna want this kind of funky property here. So let's see here. So if U is an element of V, then CU is also an element of V for all scalars C from the set of real numbers. And this property is called closure under scalar multiplication. Scalar multiplication. Okay, so again, let's go back to my set of numbers here, right? Let's pretend that I have 0, -2, and 2. And we're trying to look through this and say, okay, well, I've checked that, I can add these in any particular order. That's fine. The 0 vector that achieves this works because I'm going to define that object there to have that property. So like 2 plus 0 would give me 2, and -2 plus 0 would give me -2 still. Then we also have that the 0 vector's in there. The negative exists for everything, right? So the negative, so like this is looking like a vector space. But then all of a sudden, I'm going to ask you, okay, if I take this, does 3.86 times 2, is that inside of V, right? That's my question. Is that inside of V? Because I'm going to take a random scalar, something from the set of real numbers, and say, is that in this set? And you're like, oh, damn, no, it's not, right? And again, that makes this not an ideal candidate to use to say like, this is a vector space, right? We want to make sure that we are closed under scalar multiplication. Okay, let's see, number 7. Okay, so let's see, what else? Oh, well, we did associativity, we did additive inverses, closure under scalar multiplication. Let's do the distributive property. So we're going to say that C times U plus V should equal CU plus CV, and this is for all vectors U and V in our set V, and for all scalars C from the set of real numbers. Basically, like, this has to be true not just for 1, not just for 2, but for every single possible example. This is the distributive property. And this one has a long name, but I'm just going to call it the distributive property. It's technically the distributive property of scalar multiplication with respect to vector addition. So distributive property, I'm not going to write it out. It's the distributive property of scalar multiplication with respect to vector addition. You're like, is there another one? Yeah, there's another one. The next one kind of also makes sense. It's that if I take, let's see here, what do I want to do? If I take C plus D and I multiply it by some vector u, that is also going to equal c times u plus d times u for all vectors u in my little vector, or my little set V, and for all scalars c and d in R. So this is actually also the distributive property, but this is the distributive property of scalar multiplications with respect to what we call field addition. If you want to know what that means, you can shoot me an email. I'm not going to focus on it too much because we are on the last two properties and we're going to get through them. Okay, so number nine here is associativity for the multiplication of vectors and scalars. So it basically says that c times du is going to be equal to cd times u. Again, very common basic property that you would think you're just like, all right, this is a piece of cake. So this is associativity, basically making sure, associativity for multiplication of vectors and scalars. And it's basically making sure that these vectors and scalars are playing together nicely. Okay, that they're not going to run into any issues if you decide to multiply by a number by a vector and vice versa, or things like that, or you worry about the order, right? And then the very last one, number 10, we finally made it, is that there is this, what we're going to call this element, this vector 1 from our set V, such that 1 times V is equal to just V. Okay? This is what we call the multiplicative identity. So 0 is the additive identity. The multiplicative identity is just this thing that's identified by 1. So for instance, like the multiplicative identity in the matrix space, like a 2x2 matrix space, and we haven't talked about that, but like if I give you a matrix 1, 2, 3, 4, then the one vector is defined to be the 2x2 identity matrix, which is 1, 0, 0, 1. And you're like, this doesn't look like the number 1. That's right, because it's not the number 1. It is a vector 1, and in this case, kind of relates to the thing that I was going to say earlier that I said I wasn't going to say. This is a symbol. 1 is a symbol. This thing acts like the number 1 would in the real numbers, in the sense that if I multiply it by this matrix, I'm just going to get out the same matrix 1, 2, 3, 4. That is not going to do anything. So the identity matrix, the 2x2 identity matrix, serves as this qualifier for representing this vector 1 from that particular vector space. Okay, so these are like the 10 conditions. There's a lot of them, right? But these are our 10 mathematical commandments. These are like the, if you're going to do math and you want to be doing math that's useful and doing math where you don't have to second guess that everything is going to work or not, some mathematicians went through all of the justification and reasoning that said, look, if you have these properties, then you're in a useful space, and the math that you're going to be able to do is actually going to have real meaning, and you don't have to worry about ending up outside of the space or things breaking or going completely haywire. So, what is an example of a problem that you might be asked to do that even has anything to do with this? Well, I'm going to introduce you to something. Let me see. So, introduction to polynomial spaces. Polynomial spaces, which are vector spaces, right? It is a vector space. Okay, so a polynomial space, so I'm going to make a definition. So definition, okay, the polynomial space, we're going to say P sub n consists of all vectors, let's call them V, such that V is equal to we're going to do, let's see, how do I want to do this? A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub 0, okay? And the idea here is that the polynomial space is basically consists of every single vector, or excuse me, the polynomial space consists of a bunch of vectors that are basically every single polynomial of degree n, right? Degree n. So for instance, P2 is the polynomial space that consists of all polynomials of degree 2 or less. Okay? So n is all polynomials of degree n or less. And this is a vector space. So it turns out that, you know, all of the math that we've been able to do with you know, for instance, like quadratics, x squared minus 2x plus 1, for instance, which this is an element of the P2 vector space, of the polynomial vector space. This thing right here, right, that is a perfectly reasonable element. And it turns out that we need this to be a vector space in order for us to be able to do things like multiply vectors together, right? To be able to do, like, to define multiplying x plus 1 and x minus 3, and to be able to, like, do that and get answers that we can work with. Because you're like, oh, well, it just makes sense. Why don't we just FOIL? It's fine. Yeah, but those rules had to come from somewhere, and they come from these 10 properties. And so now what I'm going to do is now that I've introduced you to this concept, this completely new space that I just kind of pulled out of the air, it's a vector space, and I'm going to try and justify why it's a vector space. And I'm just going to kind of pick and choose some of these properties to kind of try and provide some justification. So the current goal is to justify that, or it wouldn't even be written as justify. The technical terminology would be written as like show that let's do P sub n. P sub n is a vector space. Okay, that this is actually like a collection of objects that is worth studying, that it's worth doing math in, and that we won't break anything if we try and do certain math, right? If we can think of this as a vector space, then I can denote it in this way, and long term we'll be able to do all the same math that you've been learning in this linear algebra class. That, what I just said, is like the big goal of what this section is leading up to. It's like, if you can show that something is a vector space, then we can do all of the same operations that we've been doing. We can turn things into matrices. We can turn things into vectors. We can visualize them on a graph. We can get every tool that we've ever used in this class for free, because everything we've been doing in this class has been done in vector spaces. And so this idea is that if I can show this works for some other collection of stuff, right? And I can show, for instance, that P sub n, right, this set that contains all the polynomials of degree n or less, is actually a vector space. We can do the same thing. So let's go about doing this for only some of these, just because I don't want this video to get way too long. So let's see here. Well, let's see here. Additive identity. Okay, so let's try and show this. Okay. Well, this is pretty easy. So, you know, since 0 is an element of P sub n, right? It is the element, right, 0 times x to the n plus 0 times x to the n minus 1 plus dot 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 plus 0x squared plus 0x plus 0, right? This fits the form, right? This is the form of an object in this space. And, you know, 0 plus any vector from this space, so 0 plus v would be 0 plus, remember that a random vector v in this space is something that looks like a sub n x to the n plus a sub n minus 1, x to the n minus 1 plus dot 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 plus a sub 2 x squared plus a sub 1, oops, a sub 1, a sub 1 x plus a sub 0, well, this thing is just going to literally equal the same thing, right? Because this is the number 0, and adding it to this, right, courtesy of the rules of the real numbers, right? Since we're dealing with the real numbers, we get the regular rules of, that if I add 0, I'm going to just get the same thing. We're just going to get a sub n x to the n plus ... plus a sub 1 x plus a sub 0, which is our vector v. So we have shown very generally that if I take any vector v from this set, from this polynomial space, and since we already know that, I had to show that 0 was in this space in the first place, and it is because I showed that it fits the criteria of being in this space over here, then we just did it. We went along. We're like, yeah, we wrote it all out. And it seems like such a simple thing to do, but this is what you need to do just to prove, that the fourth property, that there's an element, a 0 vector in V, such that u plus the 0 vector is equal to u. So our 0 vector is the number 0, okay, in this set. The number 0 is in this polynomial space. We're good to go. Okay, let's see. What's another one? How about this one? All right, let's do closure under scalar multiplication. All right, so let's do this one. So since the idea is, since it starts off with, we need to pick some element from our vector space, we don't know it's a vector space. So from our set, we're going to say, let's let u be an element of this set. Okay, let's pick one. All right, what do we know about u? All right, so then that means u has to be something of the form a sub n x to the n plus ... plus a sub 1 x plus a naught, and again where a1, or I guess a0, a1 ... a sub n are all just real numbers. Those are our coefficients. Okay, and so now what are we trying to show? We're trying to show that cu is in V for all c and r. Okay, so let's try and do that. All right, so we're running with the assumption, and we're going to say consider cu where c is some scalar from the set of all real numbers. Then c times u would be equal to c times a sub n x to the n plus ... plus a sub 1 x plus a sub 0, right? And this is equal to c a sub n x to the n plus ... plus c a sub 1 x plus c a naught. But I can just rewrite these as brand new coefficients. Maybe I'm going to call them b sub n x to the n plus ... plus b sub 1 x plus b sub 0, where b0, b1, ... b sub n, these are all in the set of real numbers. And this right here, because it is in the correct form, that is an element of our little polynomial space p sub n. That is in the correct form for what it means to be an element from this set. And so we're done. That's it. We have shown it. So, or we could say, so thus cu is also in p sub n, and we're good to go. Done. Right? So notice along the way that showing this one, right, showing this property right here requires what other property? It requires that we've already shown that c can distribute into all of this. All right, that I could multiply c in to individual vectors like so. So that means we would have to also go about proving the distributive property, and so on and so forth. And that's why we need all these other conditions, because they're all interlaced and they all kind of connect to each other. So this is like the general process that you go about showing that something is a vector space. I believe some of your homework questions may go about that, but the idea is that, yeah, technically, if you're in a theory-based course or you're asked in the homework, you have to start with the very first property and go just one after the other, after the other, after the other, after the other, and you start with the assumptions that you've been given, and you're trying to show that the other part is true. And you can only do it by creating a logical set of relationships that start with the thing you're assuming to be true, and then you work your way through it, and hopefully you reach your conclusion that you're trying to get. So you can't make any jumps. You have to be as thorough and complete as I am being right here, and this is theory. And the nice thing is that even though this can kind of seem tedious, it's much shorter than if I said you need to do this for every single real number ever. And you would sit here until you were blue in the face and dead, and then even after you were dead, someone would have to pick it up after you, and then they would die, and someone else would, because you would never be able to finish showing that this is true for all real numbers if you tried to do it by saying, okay, let's consider the case when c is equal to 2.3. Let's consider the case when c is equal to 2.308. Let's consider when c is, ... You wouldn't be able to actually finish the work that you're doing. So by doing it very generally in the manner that we're doing here, we have successfully shown that this holds for any vector u in our little polynomial space, and it holds for any scalar c from the set of real numbers, and we're done. So in that regard, we've actually shortcutted a lot of work for ourselves, which is really nice. Okay, so at this point, we've introduced vector spaces. I've given you a lot of criteria and just said that these are a bunch of rules that we need to follow in order to have a space that's worth doing math with, right? It's building the foundation or the structure in our little space. That way we can say, hey, this is a good place to do math. And I introduced you to your first taste of something that is not a typical vector space that you're used to. It is all the vectors inside look like little polynomials. And so that's something a little bit new. And then we went about showing that this is actually a vector space. And I only showed 2 of the properties, but you could try for practice, or maybe it'll end up in the homework, try showing the other 8 properties and making sure that you can kind of reason your way through this. So the last thing that we're going to cover in this video, and then we're going to take a small break until the next one, obviously, is what's called a subspace. So the idea here, like visually, of what a subspace is, and I'm just going to write the word up here for a second, so subspace or subspaces. The idea is that if I have some vector space V, and I take a small collection of it, right, and let's call this H. If I take a small collection of that vector space V, the question that we're curious and asking is H also a vector space? Right? This is the big question that we're interested in. Did I stick my hand in the bag and grab enough stuff and grab the correct amount of stuff that I can actually create a new vector space from those items that I've picked? So this is actually better done with a bunch of examples. Let's first kind of define what a subspace is. So definition. Okay, so a subspace. Okay, of a vector space V is what we call a subset, which is just a fancy word for a handful of the items from V. So as a subset H of V that has 3 properties. That has 3 properties. Okay. So 1, the 0 vector is in H. That's one of the properties that it needs to have. So when we stick our hand in the bag, the 0 vector needs to come with us. The second property is that H has to be closed under vector addition. Under vector addition. So that was one of the first properties that we covered, which is that if U and V are elements in H, then to be closed, that means that if I add them, what has to be true? Then their sum also has to be confined by H, right? So we have to have picked enough stuff that if we add the items together, we don't end up needing more things. And then the last thing is that we're also closed under scalar multiplication. So it's closed under scalar multiplication. Okay, and that one was that basically Cu is also in H, right? If U is a vector in H, then Cu is also in H. Okay. And if we satisfy these three criteria, then H is a vector space. And we call it a subspace of V. Okay, so that's a lot of stuff. So picture time, right? Going back to the picture up here. The idea is that when we pick this stuff, we have to make sure that not only is the zero vector in here, but we have to make sure that whatever vectors kind of come along for the ride in here, that they follow the properties that were closed under vector addition and were closed under scalar multiplication, and that the result of adding those things together, that the result isn't out here, because that would mean that I needed to take a bigger swath of stuff if I wanted to, say that this is a subspace. So a subset is just any random handful of stuff, and a subspace is if we take that random handful of stuff and it satisfies these three properties. And at this point, people are like, wait a second, hold on. Okay, you just got done telling me that we have to show, in order to show something is a vector space, we have to show 10 properties, right? The 10 properties are listed right up here. Okay, and I agree that is what I said, but I'm gonna kind of erase the stuff here really quick, and I'm gonna make an additional comment here, which is that, look, if I have some vector space V, and I know it's a vector space, I've already proven that V is a vector space. So V is a vector space. This has already been shown, proven, done and dusted. And I take some elements from here, right? I create a subset H, and I'm asking the question, is H a subspace? Let's look through these conditions really quick. Okay, this condition right here is already satisfied for H. How do I know? Because, if I pick two elements U and V here that are in H, those elements are already inside of V, right? And we already know that because they're in V and V is a vector space, that means we already know that they're commutative like this, that U plus V is going to equal V plus U. So this criteria is already taken care of. What about the next one? The same property holds, right? Like if there's a third vector here, right? If there's a third one, because they're already inside of V, right? They're already inside of our vector space V, then we already get the associativity property as well. So let's see. One that isn't necessarily true would be, and I'm going to put a red star next to this one. This one's not necessarily true because we could have picked a subset and left 0 out, right? So that one's not necessarily true. So that's one of the ones that we have to check. Number 1 is also one we have to check. And the reason why we have to check it is because even though U and V, these two vectors are already inside of V, all we know is that the result of adding them together is still inside of V, but we don't necessarily know that it's inside of H. And because we want H to also be its own little vector space, we need to actually go about and check this ourselves. We know that the sum of them won't be outside of V, but we don't know that they're going to be inside of H, or they're going to stay there. So we could keep going down this list, and you'll see that the reason why I don't need all of them is because a lot of the other properties we get for free because the vectors have already been shown to be inside the vector space V. But the one that we don't get for free is going to be the scalar multiplication. So these are the three that we need to check for. The others we get for free, and so that in turn is going to make sure that H is itself a subspace, and that's why we only have to check these three things. So I guess the best thing to do here is to just do one quick example and then kind of call it a day. So for example, let's see. So the polynomial space P1 is a subspace of P2. So show this. Okay, so we're going to work under the assumption that P2 is already a vector space, and that all we need to do is show the three criteria. So the first one is that since, again, I'm going to approach this as if I don't know anything, and I'm simply going to say that since 0, the number 0, is equal to, it would be 0 times x to the first plus the number 0, and this is an element inside of P1, and it is an element inside P1 such that if I were to take 0 plus any element V, any vector V, where V is itself an element in P1, then 0 plus this vector V, this element from our polynomial space 1, P1, would be equal to 0 plus a sub 1 x to the first plus a sub 0, which is equal to just a sub 1 x to the first plus a sub 0, and that is just the vector V. And so thus we have generally shown, so thus 0 is going to be our 0 vector, and that is an element in P1. So we have shown the first criteria, we are done. You're like, this is a lot of effort just to go and say, well, 0 is inside P1, so we're done, right? You have to go and show this. This is the rigors of mathematical theory. We have to kind of be very thorough. Number 2, that we're closed under vector addition. So I would say, all right, so we're going to let U and V be elements inside P1. Okay, so that means that, so then let's say that or I'm going to just call my U vector, I'm going to say since it's an element of P1, it looks like A1 x to the first plus a sub 0. And I'm going to call my V vector, let's call this B1 x to the first plus B0, where A0, A1, B0, B1 are themselves scalars from R. And then I would say, consider that U plus V would then be equal to A1x plus A naught plus B1x plus B naught, which I can then write as A1x plus A2x plus A naught plus B naught. And in this case, because we will have already inherited the other properties of being a vector space, we know that this first thing is going to be the same thing as A1 plus A2 times x plus A naught plus B naught. And this thing right here, we could relabel. This is just some we could call this some C1 if we wanted, and I could call this some C0 because those are just scalars, right? Those are just numbers in the set of real numbers. A naught plus B naught, just give me a new one. And so this would just be C1x plus C naught, and that is an element inside of P1. So again, we've shown that if I take any two random elements from the polynomial space of, the polynomials of degree 1, add them together, I'm going to get another polynomial of degree 1. It almost makes too much sense, and that can be the maddening thing sometimes for students. We're like, this makes too much sense, it's super easy. Of course, if we take two lines and we add them together, we still get a line. Like, duh. Yeah, but this is a theory, and there are reasons why we're doing it, so we're just going to do it. And then the last one is closed under scalar multiplication. And so I would say very quickly, let U be from P1. So then U is going to be A1x plus A0, where A0 and A1 are from the set of real numbers. And then I would say, so consider that C times U1, where C is an element from the set of all real numbers. So then CU would be equal to C times A1 x plus A0, which itself is equal to CA1x plus CA0, which of course is equal to some new, we'll call it C1x plus, we'll just call it C sub 0. I'm going to say at this step, I would have to say, let's let CA1 be equal to C1 and CA0 be equal to C0, which we can do because that's how real numbers work. And this, of course, is an element inside P1. And so we're done. And so therefore, so we can say, therefore, that's what this triangle dots mean. Therefore, we can say that P1 is itself is a subspace, right, of P2. Right, it lives inside P2 and is hence itself a vector space, which means it's a good place to do math. All right, so just kind of hurrying to the end of that because this video is getting kind of long. We're going to stop here. So key takeaways is that we want to have this idea of that we're going to start calling our spaces vector spaces. Vector spaces come with very particular properties, so not every space is a vector space. Not every collection of objects creates a vector space. In the homework, you're going to get to see some collections of objects that might look super weird, and you may not think that they're actually vector spaces, but they are, or some that look like they should be vector spaces, but they maybe fail one of these 10 criteria, and you're going to have to go through and Sherlock Holmes your way through it and figure out which one they fail or if they satisfy all 10. And that's going to do it for this video. So hopefully you think that's interesting. You think the theory is interesting. We're going to kind of continue the theory in the next video and just kind of keep getting our hands dirty. So study this video, study these axioms, maybe take a look at the homework if you have access to it, just to try and get an idea of what some of those questions look like. And then when you're ready, head on over to the next one.